Hi everyone, welcome back to our lesson 6 and our second unit in AP Calculus. This unit we've been covering continuity, the intermediate value theorem, and for the past few lessons, the derivative. Today I would like to discuss how the derivative of a function relates to the original function in terms of their graphs. So to do that, we're going to build up an estimate of the graph of f prime given a graph of f. And we're not going to go through and do the actually calculate the derivative. We're just going to estimate it using tangent lines. So we're going to use a ruler and we're going to draw some tangent lines on this graph the best we can and fill in some of the points on this table. So for the first one, we can see that when x equals 0, the y is 0 on the graph. When x equals 1, the y is 1. When x equals 2, the graph is 4. And when x equals -1, we have 1. And when x is -2, we're at 4. So those are the y values of the graph. Now we're going to find the f prime values. So let's start with, let's see if I can't make this a real small line. Let's start with 0. So if I hope you can see that, I'm drawing a thin orange line right there at x equals 0. Can you see that that line is indeed flat? So the derivative is 0 there, because a horizontal line is a slope of 0. Now let's do another tangent line, this time at x equals 1. And again, I'm just kind of estimating here. I think that's not quite right. Let's try. Okay, how about that? So I'm going to say that the slope of this tangent line is up 1 over 2. The slope of the tangent line is 2. So remember, we're making a function f prime based on the slopes of the tangent lines at different x values. These are not the y value of the graph. These are the slope of the graph. Another term for slope of the tangent line is slope of the graph. All right, let's do another one. This time at x equals 2. Well, I think that's a little too steep. What do you think? Let's make it just a little bit. Now, why are you doing that? There we go. All right, well, I think that's about as close as I'm going to make it, but I think we can see it's up 1, 2, 3, 4 over 1. Okay, so that is a slope of 4. Look at that. The slope of the tangent line is the same as the y-coordinate of the graph, interestingly enough. All right, let's do another one. Let's try x equals -1. Okay, something around there, maybe. I hope you're doing this. If you don't have a paper version, I hope you're taking some sort of straight edge. You could use an ID maybe and just hold it up next to the computer screen and get a feel for this. Because I want you to have an idea of how tangent lines interact and an ability to predict what their slopes are just by looking. It's really important. Okay, well, I'm having a little bit of trouble with this one, but I think I've got it now. Looks like it's down 2 over 1. So I will mark that for us. Down 2, so negative. And let's try at -2. So at -2, let's look like it's something like this. Oops, not quite there. There we go. Something like that. That's going down 1, 2, 3, 4, 5. That's probably too much. I think it's going to be the same as on the other side. So I'm going to, that looks a little better actually. Okay, so that's a slope of about -4. Okay, so there we have it. We've got our different tangent lines in our graph. So now what we're going to do is we're actually going to plot this curve. So I am going to just, let's see here, I'm going to pick blue and I'm going to plot this curve now on here. So when I graph x and f prime of x. I'm totaling that. So x of 0 goes to 0. X of 1 goes to 2. X of 2 goes to 4, right? X of negative 1 goes to negative 2. X of negative 2 goes to negative 4. So do you see a pattern here? It looks like it looks like it's a line, right? Right through there. A line with a slope of 2. So what appeared to be a quadratic derivative resolved down to a line. There's a couple of things I want to take note of before we leave this. First thing I want to do is take note of where is the blue derivative that I graphed, where is it above the x-axis, and what is f doing at that time? So the graph of f is doing what when the derivative is above the x-axis? Well, where the derivative is above the x-axis is all the x values where the graph had a positive slope of a tangent line. Positive slope of a tangent line means the graph has a positive slope, which means it's increasing, positive going up. So we can see that the derivative is above the x-axis wherever f of x is increasing, and is below the x-axis wherever f of x is decreasing. Also, take note of where the derivative crosses the x-axis. It happens to intersect the graph of f there, but what I want you to notice is how the vertex of the parabola is located right at the x-intercept of the derivative. All right, you have a practice problem to do. I'd like you to do your best to fill it in. Your goal is to graph f and f prime on the same axes, and to try and make some connections between the two. If you're going to draw the tangent lines on the graph, do it lightly like I did so that you can still go back later and fill it in. Okay, so I have drawn several tangent lines. I don't know if you can actually see all of them very well. You may have drawn different tangent lines than me, since we were not given x values to use. You had to pick your own. And you might get a slightly different answer. Without having the actual equation of f and without actually calculating the derivative, we are only estimating, but we're trying to look for larger patterns to develop. So I am choosing some x values. I'm going to try negative 1, 2, 3, 4, 5, 6, 7, 8. I'm going to use negative 8 here. The y coordinate there is negative 1, 2, 3, 4, 5, 6, 7. And the slope of the tangent line, as I calculated, if you look at this thin orange line, is up 1, 2, 3, 4, 5, 6, 7, 8, 9 over 1. So I'm getting a very steep tangent line there. Now, then let's go over to negative 1, 2, 3, 4, 5, 6 on the x. Negative 6, the y value has climbed quite a bit. 1, 2, 3, 4, 5, 6. And so look at our change in our y values, quite a dramatic change. Well, that's also because the derivative was such a big value. We would expect a change of close to 9 units for every one, and we moved 2 over. So 6. Now the slope of my tangent line there is not nearly as steep. I drew it. It's hard to see, but it's right here, going up 1, 2, 3. Let's see, 1, 2, 3, about 4. So it's much less steep. Then at negative 1, 2, 3, 4 on the x, we're up at a height of 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that 10 already? Yeah, I guess so. All right, so we're all the way up there at a height of 10. And the slope, although I didn't draw it very well, if you can see it's going up a little too much, it should be flat. That is a flat tangent line. That is a slope of 0. Then we start going negative with our slopes. So right around here at negative 2, we have fallen down to 8. And my tangent line there is somewhere around, it looks, I'm going to say like negative, maybe I'm getting around negative 2. Okay. And then if I travel over to an x value of 0 and a height of 4, I'm still getting a slope of negative 2. It seems like somewhere in between there, it kind of got steeper and then not as steep. So there's kind of like a get steep and then get less steep all of a sudden. And it's definitely getting less steep as I go around this curve here. And I can get to, at 2, I have a y coordinate of 2, and again a slope of 0. And then this curve here has a slope of 1, 2, 3, 4, 5. It looks like, right? 1, 2. Well, maybe not. We're right here. We go 1, 2, 3, 4. Yeah, just 4 there. And that is the x coordinate of 4, I think, and a y coordinate of 3, 4, 5, 6. Okay, we're finally ready to plot our derivative. So at -8, our derivative is at 9. Then at -6, we're at 4. Then at -4, we're at 0. At -2, we're at -2. At 0, we're still at -2, it looks like. Then at 2, we're back at 0. And then at 4, we're at 1, 2, 3, 4. So what shape is this making? Well, I think it's making some sort of quadratic kind of shape, like a parabola. And I bet it dips down a little bit and then starts coming back up and goes like that. So, key takeaways. Notice that this, what is called a local maximum, it's a maximum highest point in a neighborhood around other points, occurred when the derivative was 0 and where the derivative graph crossed the x-axis. Now over here, same thing. But this is a local minimum, and it's occurring where the derivative crossed the x-axis, or where the derivative has a 0. So we could see that the graph is actually increasing in 2 different locations. The graph is increasing over here for all these x values to the left of -4, the derivative is positive and the graph is going up. And for all the x values greater than 2, the derivative is positive and the graph is going up. In the middle, in between -4 and 2, is when the graph is decreasing and the derivative is negative. All right, let's do another one. All right, so we're going to estimate several different values of f prime. So let's do that. Let's draw, well, what kind of tangent line would I draw there? You know, maybe it's flat, maybe it's really steep, like in between the two. But let's come back to that, and we'll have to think about that. I'm going to start at, let's see here, 1 comma 3. So at 1 comma 3, I think I can estimate that tangent line pretty readily. Might be a fraction though, I'm not sure. I'm not sure we're going to get a nice whole number there. Well, that's too flat, not steep enough, right? Okay, what about, well, okay, maybe we do get a whole number. I'm thinking a 2. Thinking 2. So at x equals 1, the graph has a y value of 3, and the derivative, the slope of the tangent line, is 2. All right, let's try another one. Let's try at x. Where's a nice lattice point? Kind of, not really very many of them. Let's try this one here. Okay, so that point there is like up 1, 2, 3 over 2. So definitely a little flatter, but not much. So derivative is 3 over 2 at x equals 2. And my y value was like 1, 2, 3, 4. I don't know. Let's say 3.9. Or if you want to put 4, that's fine. We can just round it. All right, let's do another one. What do you think? Maybe over here? That is a slope of 1. So at x equals 1, 2, 3, 4, 5, we have a slope of 1 for our tangent line, and the y-coordinate was 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, we can also check -1, -2, and -5. But do you see the symmetry here? So I'm going to say that these are the same y values because it's got y-axis symmetry. And if you draw these tangent lines, we're going to get the exact same tangent lines, but now they're negative. And I'll let you fill those in if you so choose. So let's think about what's happening if we could zoom in on this graph and start getting tangent lines closer and closer and closer to the x value of 0. Well, as I zoom in, what's going to happen is you're going to see this little kind of V here is going to become more and more like this. Oh, that's not how I meant to draw that. Like that and like that. And so on the left-hand side of 0, you're going to be getting tangent lines that are getting closer, more and more negative. In other words, going to negative infinity. But on the other side, you have tangent lines that are getting steeper and steeper and steeper as if they're going to positive infinity. So I'm going to say that at x equals 0, the y value is 0 and the derivative does not exist. What kind of does not exist? It is or it's undefined, we could say. The derivative is undefined because it is that those slopes are going to negative infinity in one direction and positive in the other. And that's going to help us graph. So let's do that. Let's plot some points. 1, 3. Oh, sorry, that's the y value. 1, 2. We're graphing the derivative here. So let's say, hey, there's already a point there. 2 had 3 halves, right? So 1, what is that, 1.5? Yeah, okay. And then at 5, 1, 2, 3, 4, 5, we're at 1. And what we said was that as you get steeper, closer and closer and closer to x equals 0, you're getting steeper and steeper and steeper. So the rest of these values are going to be up here. And this line here, I think we're going to assume that it's actually going to level off, and make this curve like this as you go off towards infinity. So I think it's reasonable for us to conclude that this has got some sort of horizontal asymptote to it. Again, these are estimates. We'd have to have the equation to know the real thing. Now let's go ahead and plot the other side of our derivative. So we have -1 goes to -2. -2 went to -1.5, and -5 went to -1. And we said that as you get closer and closer and closer to x equals 0, you're getting more and more negative. You're getting super negative values, so we're shooting down towards negative infinity. And so there we go. So notice the asymptote on f prime, right where that what's called a cusp occurs, a real pointy value. So this brings up a very important discussion. And that is a discussion about continuity. So what I'd like to do is I'd like to establish that in order for the derivative to exist, your curve has to be 2 things. 1, continuous, and 2, it has to be smooth, or what we call local linearity. So I'm going to pull open a Desmos graph, and I want us to take a look at some places, some graphs that do not have local linearity and some that do. All right, so I just got a calculator here to graph. So let's take a look at y equals x squared. What local linearity is saying is that if I zoom in anywhere on this graph where there's local linearity, if I zoom in, I should get something that looks like a line. And it is that line that you have there that when you zoom in, that is that tangent line. So if I zoom in here, I'm going to eventually get what's going to look like a line. So you see on my screen, after I've zoomed in so much, my screen becomes like the line itself. All right, let's try right here at this vertex. We said the derivative was 0. Well, if I keep zooming in, what's going to happen is it's going to look more and more flat, and that's what a tangent is basically looking at the graph super zoomed in. You can see there's that horizontal line, right? Okay, so let's look at one like the graph we just had, which I want to say is kind of similar to that. So if I look in over here, again, I'm going to get that, I'm picking this spot right here. I'm going to get a tangent line. You see that line there? Because it's continuous and smooth. Now, what happens when I zoom in here? Well, I'm getting two different lines as I zoom in. They are getting closer together, I think. But now it's a vertical line, one going up and one going down, and there's no line down here. So that is not a tangent line. Let's take a look at another one that does not follow local linearity. So how about the absolute value of x? If I zoom in anywhere on this graph besides one x value, I'm always going to get a line. But what happens when I zoom in right here? Well, absolutely nothing happens. Do you see that? I mean, I'm having absolutely no line shape. I'm still got that V no matter how much I zoom in. This point here is not smooth. It does not have local linearity. All right, and let's take a look at this one. How about the cube root of x? Well, let's zoom in there. Does that have local linearity? Sure looks like it, but what kind of line is that? Well, that's an undefined slope, right? So we're going to say the derivative doesn't exist there either. Not because it's a cusp or because it makes a point, but because it is a vertical line. Although that, I hate saying derivative that exists. It's an undefined value, but it's a very important undefined value and that has lots of practical applications. Okay, so that was a nice little discussion. Let's formalize this just a little bit. Clean this up, bring over our notes. All right, so a function f is said to be differentiable at some value c if the derivative of x exists at x equals c. In order for a function to be differentiable at x equals c, the function must be both continuous at c and have local linearity at c. In other words, the graph must be continuous and smooth. So I want to point out kind of the old rectangle square relationship. You know what I mean by rectangle square relationship, because we got one here. What this is saying is that every function that is differentiable at c must be continuous at c, because that was a requirement. But not every function that's continuous at c is differentiable at c. So differentiability is a stronger description of continuity. And so if you know that a function is differentiable at a value, you can make a conclusion that the function must be continuous by simply saying because it's differentiable. Differentiability implies continuity, but not the other way around. All right, let's take a look at this set here. Okay, so what I want to do is for each, I want to determine x values where the function is not differentiable, and we'll explain why. So this function here is not differentiable at x equals 2. At x equals 2 because why? A sharp point, right? Or just quite simply, it does not have local linearity. What about this one? Well, this one's not differentiable at x equals 2, and the reason why is because it's not continuous there. Or you could say there's an asymptote. But that's basically the thing, is that wherever you're not differentiable is because you're either not smooth or you're not continuous. Or, in this case here, there is a third. This is not differentiable at x equals 1 because the slope of the tangent line is vertical. So you would be able to if you calculated the derivative here and then tried to calculate it at 1, you're going to get a divide by 0 error, which is of itself very interesting, and we'll oftentimes use that to help us understand the graph. All right, and at this one here, x minus 1 to the 2/3, we were just looking at this very thing. There's a cusp. It is not differentiable at x equals 1 due to a cusp is what they call that. CUSP, kind of a fun word, but not smooth. You must be continuous and smooth. So we have discussed what it looks like for a function to be not differentiable in a graph. We talked about being able to zoom in and you should see a tangent line. If you don't, it's not differentiable. It's time for us to discuss it in terms of the true definition so we can really see. I want to use the alternative definition of derivative. I think it's going to be a little bit easier for the task we have before us here, but we could certainly show this with either one. So we're going to use the alternative form of the derivative to find the derivative of x equals c if it exists. So I've got a function and a c value, and hopefully we see some things that kind of explain when the derivative doesn't exist through the calculus. All right, so here we go. Do you remember the alternative form? It is the limit as x approaches c, which in this case is 3, of f of x minus f of 3 all over x minus 3. So we have the limit as x approaches 3 of the absolute value of 2x minus 6 minus, now if I plug in 3, I get 6 minus 6 is 0 over x minus 3. Now this absolute value bars, we need to understand that the absolute value of x is defined to be negative x when x is less than 0 and positive x when x is greater than 0, and it's 0 when it's 0, so I can put a bar on one of those. Well, they already told us that c, by just plugging it in, c equals 3 is exactly when 2x minus 6 equals 0. So what I'm going to do is I'm going to split this apart. I'm going to say that this is the limit as x approaches 3 from the left. This is negative 2x plus 6. You see how I distributed a negative to the 2 and the negative 6. And then minus 0 is just 0. And I over x minus 3. So that's that one. And then I also need to find the limit from the right. Can't just plug in. Can't just do algebra because it's not a nicely behaved function. It's a piecewise. Absolute value is piecewise. The limit as x approaches 3 from the right would be 2x minus 6. You just take the positive and then x minus 3. So this is going to factor to a negative 2 times x minus 3 all over x minus 3. And I get negative 2 when I cross this out in the limit as x approaches a value of a constant is simply that constant. Now let's go over here. Factor out of 2. Those reduce. And the limit of a constant is simply a constant. So it's 2. So what we have is that the limit as x approaches 3 from the left is negative 2, but as x approaches 3 from the right is positive 2. What does it mean when the limit does not approach the same value when you take a left hand and a right hand limit? It means that limit does not exist. So since this limit does not exist, we would say that f prime of 3 is undefined. Or some people will say the derivative does not exist there. Whatever it is, it's not differentiable. And we don't need to worry too much about the vocabulary of that in that regard. All right, let's go on to another example. And we shouldn't be surprised that it wasn't differentiable. We know that that shape there's going to be a V. That V shape is not differentiable there. Okay, we got f of x equals x minus 2 to the 2/3. Let's do it. All right, we know that the derivative, we're using the alternative today, right? The alternative definition of the derivative is the limit as x approaches the c value of 2 of f of x minus f of 2 all over x minus 2. My f of x is x minus 2 to the 2/3. F of 2, if you plug that in, you get 2 minus 2 is 0. 0 to 2/3 is 0. All over x minus 2. Okay, I will now... I'm going to reduce this. I'm going to say x minus 2 to the 2/3. That is, and this is x minus 2 to the first. I can simply subtract exponents here. I've got the same base. So 2/3 minus 1/3 is a negative 1/3. So it becomes x minus 2 to the positive 1/3 on bottom. Now if I plug that in, what you get is 1 over something going to 0. So this must be an infinity. And we can look and see which one. If you take the limit as x approaches 2 from the right, you would be dividing 1 by a number. When you plug in a number just bigger than 2, 2 minus a number a little bit bigger than 2, minus 2 is a positive number. So from the right-hand side, the limit as x approaches 2 from the right is infinity. The limit as x approaches 2 from the left, though, is going to be a little bit different. It's going to be plugging in a number slightly smaller than 2 and then taking the cube root of that is going to be a negative infinity. So this does not exist. And as it turns out, having a limit, even if they both went to infinity, we would say it's not differentiable. It would be, an infinity is not a value for a derivative. All right, we have another one. All right, f of x equals x squared plus 2 for x less than 1, and f of x equals 3x for x greater than or equal to 1, and when you know it, we're going to check the differentiability at 1. So we're going to have to take the limit. As x approaches 1 of f of x minus f of 1 all over x minus 1. Well, what is f of 1? F of 1 is 3 because you used the bottom branch. So f of x would be x. Ooh, wait, hold on a second. I don't want to plug that in yet. Let's leave that as f of x because that's going to take some thinking. Minus 3 over x minus 1. So let's take the limit from the left and the right. Also, we should probably check this, make sure this is continuous, because if it's not continuous, then this doesn't really matter. I mean, I guess if it wasn't continuous, well, you wouldn't get, I don't think, yeah, I mean, you could actually think it was you could possibly think that the derivative existed when it didn't. So we probably want to double check that. But if you plug in 1, you get 1 squared is 1 plus 2 is 3. You plug in 1 here, you get 3. So this definitely is continuous. The question is it differentiable? All right. So I'm going to have to find the limit, because it's piecewise. I'm going to have to break this apart and find the limit from the left and the right. So the limit from the left would be using this top equation. And that would be the limit as x approaches 1 from the left of x squared minus 1 over x minus 1, which is the limit as x approaches 1 from the left of x minus 1 times x plus 1 all over x minus 1. So what does that equal when you plug a 1 in there? It's going to be a 2. So from the left, the limit is approaching 2. Let's try from the right. From the right, my f of x is 3x. So it'll be 3x minus 3 over x minus 1. Factor out of 3. The x minus 1's cancel, and I get the limit of 3. The limit of a constant is just a constant. But 2 does not equal 3, so this does not exist. It is not differentiable at x equals 1. And what's happening, if you were to look at the graph, I'll tell you what, I wonder if I still got my Desmos open. I do. Let's look at the graph. because this one's worth talking about. We have f of x, and in Desmos, piecewise has to be put in these curly brackets, and you actually put in the condition first. So I do x less than 1, then colon x squared plus 2, and they have examples, and you can easily look this up if you're ever trying to do piecewise on it. Then you put a comma, and you put your next condition, and then colon 3x. So I want to point out that this is definitely connected here at x equals 1. There it is, continuous. Now let's start zooming in here. Now they were close, right? They were close to local linearity, but it's not. Can you see that it is not? Let me turn on some, maybe I can. Can you see that this has a slope of up 3 over 1? This has a slope of up 2 over 1. There's a cusp here. They're not the same. So the derivative does not exist. All right, that is all for today. See here, we have a little bit more to do with the derivative. I want to look at some more, kind of some classic AP problems next time, and then we will really delve into derivatives with data, which is a huge part of the AP curriculum. So that'll be super important. I look forward to sharing it with you. Until then, take care and study hard.